Okay, so once we've hit the switch to solution button and we see this screen right here, we can begin setting up the solver. What that means is getting all the settings correct, making sure that it's solving the fluid in the right direction, the right speed, over the right walls, etc. So first thing we want to do is visualize our mesh and make sure that the size and everything is correct. So if we go to boundary conditions, and we draw, let's say we draw the rear wing E1, E2, E3, and then plates. We'll draw those. It's called display in Fluent Solver. I don't know why they didn't keep the naming the same. But there it is, and then we can zoom into that. So that's our rear wing. It looks okay. But if we hit the ruler icon right here, this icon, we'll see that our rear wing is actually about 1 kilometer long. And that's because there's a funky quirk in Fluent where it reads whatever mesh you made, it reads it in meters, whereas we made it in millimeters. So there's a very easy fix, but just always make sure you check this length right here, because we do not want 1 kilometer long rear wing. So if we go to scale right here in the task page, and then we can either specify the scaling factor or we can convert units. So mesh was created in, we'll go millimeters, and you'll see it scales everything down by 1,000, and we'll hit scale. There we go. So now we'll close that, refresh this view. So if we right click on these again and go to display, we'll see that it suddenly goes very, very, very small. We'll zoom into it again, and you'll see the wing is now about 1 meter long, which is what we want. So that's the first step you should always do. Just make sure that the length is correct, because you'll get very, very dodgy results otherwise. Okay, so once we've done that, we can then move into all of the setup. So first thing we do, we go into models, and none of them concern us for fluid flow except the viscosity. If you're also looking at like any heat, then you might add the heat exchanger or any other energy models, but we only want, for just pure aerodynamics, we only want the viscous. So we'll double click that. It'll bring us a window. The standard model that we use to model viscosity and turbulence is going to be K omega SST with curvature correction. So tick that right there. All of these numbers, you'd have to know a lot more about CFD, more than I know, to change, because those are all about the math that actually occurs. But everything else is fine as it is. So we'll hit OK. And that's our model done. Close models. Next up, we're going to materials. Here, we just want to double check that the fluid is air. That's all we want. The standard air that is in Fluent is more than fine for simulating what we want. Solid doesn't matter because we're not simulating any solids unless you are simulating some kind of heat exchange or energy, in which case you need to set what your solid is to make sure that the heat exchange is accurate. Cell zone conditions, we just leave as they are. Just double check that it says outer BOI to make sure that that is our fluid, but everything else we can leave as it is. And boundary conditions, this one right here. This is the big one. So we have to set an inlet, an outlet, the slip walls, the symmetry plane, and all of our rear wing faces as different kinds of boundaries. We'll start with the inlet because that's the easiest. So we'll go down to inlet. It'll be under wall to begin with because everything is assumed to be a wall. We will right-click inlet, and we'll go to type, and we'll change it to a velocity inlet. Once we click that, it'll bring up a window where we can set the terms for the inlet. So we want it to be obviously a certain velocity magnitude, which starts out as 0, and a certain direction, which in this case, we can see down here, is the positive x direction. So we want flow for going left to right. So instead of magnitude normal to boundary, we're going to do magnitude and direction, or we could even do components. It's up to you. I usually do magnitude and direction, because the way we set up our geometry is always going to be that the flow is in one x, y, or z. It's never a mixture of in-betweens. So we want velocity magnitude to be 22.22 meters per second, because that equates to 80 kilometers an hour, which is what FSA wants the simulations to be run at. And we want it to be in the x, so 1 in the x, 0 in the y, 0 in the z. All of these can be left as they are and apply. And that's the inlet function done. You can see now we've created a little inlet box here. and the inlets inside it. Now, we'll go back to wall. Next, we'll do the outlet. So right-click on outlet. This is why it's crucial to have named all of these name selections, because if they were just named as numbers, it'd be really difficult to tell which is what. So go to type and change it to pressure outlet. Now we want the pressure at the outlet to match atmospheric pressure. So we'll set gauge pressure to 0, and that's all we have to do for the outlet. Hit apply and close. We've now created an outlet menu. Then open the walls again. Next, we'll do the symmetry plane. So right-click symmetry. This is very, very easy. Go to type and then set symmetry. Nothing else has to be done. It just creates it by that because there's no options for symmetry. It just is a symmetry plane. Right. And finally, we'll go to the slip walls. So these are the walls surrounding our box that aren't necessarily an inlet, an outlet, or a symmetry, but they are still a boundary. So what we want to do is right-click slip walls and then edit. They are technically walls, so we're going to leave them as type wall, but instead of having them be a regular wall, we're going to specify 0 shear, so 0, 0, 0, which means that flow can just slide off the walls with no friction, essentially meaning that they're just like an invisible boundary where it won't affect the airflow in any way except stop it from going outwards. And that's all we have to do here. So we'll apply and close. All of the other walls, so our airfoils, our end plates, our gurney, and our trails, are going to be regular walls that the flow needs to flow in and around, and they have to be walls that slow down the airflow and have friction effects on the air particles. Hence, they stay exactly as they are. But if you have simulating, for example, a front wing, and you had a ground, then you would set that as a moving wall. So I'll give you an example. Let's pretend the E1 curve was the ground. We'll go to edit because it's still a wall. Then instead of a regular wall, which will come up here, we're going to set instead moving wall and set all of the moving parameters. You can even have it rotate if it was a tire, in which case you set rotational parameters like the axis of rotation and the speed of the rotation, etc. And if it's just a regular translational wall like the ground, you just set the speed and the direction of the movement. But we don't have any of those for a rear wing simulation, so we'll set that back to a stationary wall, apply, and close. And that's our boundary conditions done. So let's close those back up, close that back up, and move down to, we have no mesh interfaces because we don't have separate zones, so we'll ignore that. Dynamic mesh is if you're running a transient simulation with meshes that move. We don't have that, so we'll ignore that. Next is reference values. So we'll double-click reference values. This is for calculations that Fluent does, like the CL and CD, which you could do yourself manually. It doesn't take very long, so this isn't a necessary step. But I think it's good to just get in the habit of doing this so that it is easier if you do want Fluent to calculate it. So we'll just compute from the inlet, and it'll give us all the values we need right there. And that's done. You'll see it's changed the velocity to be 22.22. So the reference velocity for any CL or CD calculation is this, reference area, reference density, etc. Everything it needs is right here. So then we'll move down to, we don't need reference frames or named expressions. Move down to methods. Now this is the way in which the solver solves the equations. Because it solves them numerically, it never solves them exactly. So it solves them numerically, and you can set which kind of procedure to solve them with. So for each different, I guess, the component of the flow, so pressure, momentum, etc. So as it is right here is what you're going to want for most 3D simulations. So you want a coupled scheme. Your gradient should be least squares, and everything else should be second order. If you come across any research or any papers that change this and you think that's right, go ahead and test it and see what the differences are. But for now, I would say use these guidelines as your go-to, and make sure that pseudo-transient and warped phase gradient correction are ticked. So pseudo-transient means that it's not going to take a pure steady state solution. It'll take into account very, very small fluctuations, I guess, in the flow, because it's never going to be perfectly steady around a wing that's very turbulent. So tick that and then tick that. So that should be your methods. Your controls, you can double click. We're not going to change any. But once you learn more about CFD and how it solves, you can change some of these relaxation factors, which relate to how strict or how stringent the solver has to be in solving from one iteration to the next for all of these flow components. I would leave them as they are, but once you get to know more, you can change these to be more relaxed or less relaxed. Right, report definitions. Double click that. These aren't necessary because you can do all of these post solving, but it might be a good habit to get into. Just do them pre-solve. So these essentially, you can calculate the force exerted by the air on whatever object you're doing, or many other parameters of the flow. We'll just stick with the force. So let's calculate, let's say, the drag on the rear wing exerted by this simulation. So we'll name it drag in newtons. We can choose between the drag coefficient or the drag force. The coefficient will solve using the reference values that we set before. So if you didn't set any of those, just calculate the drag force and then work it out yourself. So that shouldn't be too difficult. The force vector for the drag is going to be in the positive x direction because it's the same direction as the flow. And then select all of the walls which you want your drag to be computed about. So we can select all of them, but make sure that slip walls is deselected because we don't want, even though it won't have any force, we don't want to calculate the drag exerted on the slip walls. We just want our rear wing in its entirety. And then we can hit compute. You don't want any of these for now, but we'll hit compute. Okay. And once we've solved the whole case, you can see you'll come back into here, right click. Just click it once and you can hit compute down here once we've solved. And it'll tell you what the drag is on the rear wing. And I'll show you another way of doing that afterwards. But you can also add the lift or any other parameters in here. So we'll close that. And then the last few things to do would be to initialize and run the calculation. But before we do that, we just want to check the mesh just to make sure there's no issues. So if we perform a mesh check right here and go to the console, it should come up with no issues found. If it does come up with issues, it'll come up with a dialog box. But since it hasn't, it just says done, which means it found no glaring issues in our mesh, which is good, which means we can now go ahead and start initializing and then solving the calculation. So we'll double click initialization. I usually prefer standard initialization because I'm not quite sure what hybrid does, but you can do both. It's not, both work. I just prefer to know what's going on. Initialize basically gives initial values to each cell in the mesh, so that the first iteration doesn't just go blindly off of no values. So we'll compute from the inlet. So all of the cells in the mesh will get a reference value computed from the inlet. And that's a gauge pressure of 0, x velocity 22.22, and these turbulent and specific dissipation rates. And we'll go ahead and hit initialize. It'll take a second, and you'll see in the console it comes up should come up with done. But once the wheel stops turning, it means it's finished. And now we can go ahead and double click run, and we'll come up with the last menu. So if you don't initialize, it won't be able to run. It'll tell you if you try to click one without initializing, it says, do you want to initialize first? Because you have to initialize. So yeah, that's just another step. Now, before we hit run, it's also good practice just to hit check case, and it'll tell you if you've forgotten anything before running. So we'll hit check case. And in this case, no recommendation to make. So we've done everything we need to do. If, for example, you hadn't checked your mesh, it'll tell you you might want to check your mesh. Or if you've set some weird, let's say, boundary conditions, if you have no inlets and a lot of outlets, for example, or if you've set maybe some weird combinations of models, it'll tell you might want to have a look at that again. But we're good for now. So finally, to run, we have to set these parameters. So you just want to set the number of iterations. This would be if you have transient simulations. You want to set any of these. For us, we're fine with what they are. We just want to set the number of iterations to be somewhere around 150 for a rear wing. You probably get away with 100, but 150 will definitely make sure that you've solved it to a good extent. If you have a full car, maybe set this to 200. If you have something like maybe just a sphere, you can set it to 50 or even 25. And then we're good to go. Now, before we calculate, I would recommend saving the case. So that saves all of these settings and the mesh in one file, so that next time if it, say, the calculation failed, you can just reopen this setup and not have to do anything except click calculate. So to do that, we go File, Write, Case, and we'll just name it something like before solve. And cas.h5 is just the extension for the case file. And we'll hit OK. Again, it'll take a second to solve because it's quite a big file. There we go. We're finished. So now the last thing we're going to do is just hit calculate. And then it'll begin. It'll bring up a new window in here where it'll show you, if you go to the graphics, it'll show you a graph of the solving, I guess, status. So it'll show you how much conversions it has done for each iteration. So the way it solves, it basically tries to minimize the error in the solution, right? So for every mesh cell, it'll solve it once and then iterate and solve it again, and it'll check the difference between the previous iteration and the last iteration. And the smaller that gets, the closer you are to the solution. And so you'll see here a lot of these colorful lines will pop up, start quite high, and then go lower and lower and lower as the convergence gets smaller and smaller and smaller. If they all go below 1e-3, it stops the solution automatically and it's done. But it doesn't have to all go below e1e-3. It might stop at like 1e-2 around there. That will still be fine. But yeah, so this will definitely take a second. You can see the lines start to appear. We've only had 2 iterations so far. So they'll look quite crazy at the beginning, but by the time it stabilizes out after like 20 or 30 iterations, they'll start going on a downwards trajectory. But I will stop the recording and show you guys what it looks like at the end.